Now the various vibratory systems are critically damped system, overdamped system and underdamped system. So in case of the critically damped system, zeta is equal to 1 because we know that the definition of zeta is nothing but it is C upon CC. So for critically damped system, replace this C by CC. So value will be equal to 1. So the value of zeta that will obtain in case of critically damped system is 1. So when the value is equal to 1, it is known as critically damped system. If value is greater than 1, correct? So in case of overdamped system, C is greater than CC. So this ratio will be greater than 1. Then it is overdamped system. Whereas in case of underdamped system, C is less than CC. So that ratio comes out to be less than 1. Then it is a underdamped system. So critically damped system means what? Suppose the cycle start from 0, the amplitude become maximum over here, again becomes 0 at this point, reaches magnitude, reaches to the maximum value in the maximum amplitude in the negative cycle and again becomes 0. So the cycle is completed within the optimum period of time without doing much oscillations further. So if the oscillations continue, then it is not the critically damped system. So this is the required damping part or damping system for us. The vibration should not be large in certain cases. So this is the required position. Now, in case of the overdamped system, you provide the damping in such a way that number of springs are more, dashpot will have higher viscosity, viscous liquid or viscous oil. So in that particular case, the suppose the cycle start from 0, becomes maximum, then again becomes 0, maximum at the negative part of the cycle, and then it will not complete the cycle at all. So it will just halt over here. So the vibratory cycle is not getting completed over here. So that is known as the overdamped system. So in that particular case, damping coefficient of the actual system is greater than its critical damping coefficient. This is desirable in certain applications. So those applications we'll see afterwards. Now in case of the underdamped system, the amplitude for the first cycle is like this. At the start of the second cycle will be like this. So initially it was like this and now it has decreased to this part, correct? So vibrations, they are continuing over here like this. We have closed the cycle over here, but it may continue on the next part also, correct, like this. So this is sometimes undesirable, that vibrations should not be continuing, the vibration should be damped. So if you draw the curve joining this peak part of this, then this particular curve that will get is the, so if you join this top peaks of this cycle, amplitude of this cycle like this, and then further if you join this and if you join these points, then you will get the curve which is in the exponential fashion. So it is also known as the logarithmic decrement or exponential decay. So this is the underdamped system, which may be desirable in certain cases but not at all in all the cases. Now we have to derive the expressions for the overdamped system, for underdamped system and for critically damped system. So for that we will require the knowledge of S1 and S2, which we have already derived in terms of zeta. So S1 and S2 values we have already derived in the previous lecture, those we have written, and now these are the real and different roots, and its general solution is also known to us, that is A e raised to s1t plus b e raised to s2t. Similarly, for critically damped system, value of zeta is 1. Here, value of zeta is greater than 1 for overdamped system. For critically damped system, that value of zeta is equal to 1. So if you substitute zeta is equal to 1, then it will be minus 1 into omega n, that is minus omega n, because this term is 0. So we can say that in the first case, we are having the overdamped system where zeta is greater than 1. So this will be the real and different roots. Whereas here S1 and S2 both are having the value, because this square root term is 0, 1 square is 1, 1 minus 1, that is 0. So it is minus 1 into omega n. Over here also it is minus 1 multiplied by omega. So these are the repeated real roots. And for repeated real roots, the general solution is C1x plus C2. That is, this is from our M3 part. So in place of C1, or rather in place of C2, we are having A. C1, we are having B. In place of X, our variable is T, and e raised to the root that we are having is minus omega n. So it is e raised to minus omega nt. So this is the general solution for critically damped system. So once again, try to understand. For critically damped system, substitute zeta is equal to 1. So this square root term will vanish. So it is only minus 1 multiplied by omega n. That is minus omega n. And for repeated real roots, the complementary function is given by c1x plus c2 e raised to mx. So c1x plus c2 we have written in c2 plus c1x form, c2 plus c1x e raised to mx. So in place of c2, our constant is a. In place of c1, our constant is b. And in place of m, we are having omega minus omega n, because our root that we have obtained is repeated root that we have obtained is minus omega n. For overdamped system where we are having real and different roots, it is c1 e raised to m1x plus c2 e raised to m2x. So in place of y it is x, in place of c1 it is a, in place of m1 it is s1, and here in place of c2 it is b, and m2 another root is s2. So these are the two roots s1 and s2 which we can substitute over here, and their analogous part is m1 m2 in our m3 part, or mathematics engineering mathematics part. So for underdamped system, zeta is less than 1, so we can say that S1, S2 will be equal to minus omega n plus or minus. Now you can take minus sign common. So zeta square minus 1 will be equal to, if you take minus sign common, it will be 1 minus zeta square. So omega n as it is, this is minus zeta plus or minus. Now minus means minus 1, and minus 1 is replaced by I square. So we are getting the complex root over here. So this is important part. So this is square root of I square means I. So what is the root over here? Minus zeta omega n plus or minus multiply by this omega n inside the bracket. So it is I omega n square root of 1 minus zeta square. So in the square root term, we were having zeta square minus 1. So just we'll go back to our previous expression of S1 and S2. So this is the term which is now important for us. From this term, we have taken negative sign common. So if you take negative sign common from that, then it will be 1 minus zeta square instead of zeta square minus 1. So this is the important part. Now this minus is nothing but minus 1, and that is replaced by zeta square. Rest of the terms are as it is. And this square root of I square is nothing but I. So this is minus zeta plus or minus I square root of 1 minus zeta square. Now multiply by this omega n inside the bracket. So it is minus zeta omega n plus or minus, again multiply by this omega n inside the bracket. So it is I omega n 1 minus zeta square. So as these are the complex roots, so this particular term omega n multiplied by 1 minus zeta square is known as damped frequency, because it is having the damping factor which is involved in it, and it is multiplied to the natural frequency. So this total term is replaced by a single term, that is damped frequency omega d. So if you recall this is nothing but our complex root. So S1 is minus zeta omega n plus I omega t, and H2 is minus zeta omega n minus I omega t. And as these are the complex root, we have to use the, so this is the real part of the solution or real part of the root, that is minus zeta omega n, and omega d, this particular I omega d is the imaginary part. So we can say that alpha is nothing but minus zeta omega n, and beta is nothing but omega d in this particular case. And for complex root, what is the complementary function that we have seen in our engineering maths or M3? It is e raised to alpha x c1 cos beta x plus c2 sin beta x. So replace this by our variables. So in place of alpha, we are having minus zeta omega n, alpha and beta we have written over here. In place of x, it is t. C1 cos beta is nothing but omega d. X is replaced by t. Here also beta is nothing but omega d, and variable x is replaced by t. So this is the value of complementary function. So in place of yc, our variable, or in place of y, our variable is x. Now let us replace this c1 by another constant m sin psi, and this c2 by another constant, that is m cos psi. So therefore our expression will get modified. So this e raised to minus zeta omega nt as it is. In place of c1 it is m sin psi cos omega dt as it is. In place of c2 it is m cos psi sin omega t dt. So we are taking into consideration this particular form so that we can derive the expression in terms of simple harmonic motion. So that derivation is very complicated and we'll derive it further. Now take m common from both these terms. So if you take m common from this, it will be sin psi cos omega dt plus cos psi sin omega dt. So this is the formula of sin alpha cos beta plus cos alpha sin beta, that is sin alpha plus beta. So if you remember, this is the form of simple harmonic motion. So this is the amplitude of the vibration and this is the direction or frequency part of the vibration. So first part, so it is a vector quantity. First part will represent the magnitude of the amplitude and this is the frequency part of the amplitude of the vibrations. So this is the important parts. So these are the general solutions for critically damped system, overdamped system and underdamped system. So in case of overdamped system, we are having real and different root, whereas in case of critically damped system, we are having repeated root, whereas in case of the underdamped system, we are having the complex roots. So this is the way of representing the displacement, which is a vector quantity in terms of its amplitude and direction, and that direction part is represented by frequency of the vibration in this particular case.